We're going to be going over 3 different types of radioactive decay: alpha decay, beta decay, and what are called gamma rays. To start off, we need to figure out a couple of key terms that correspond with radioactive decay. So you have radioactive isotopes, and those isotopes are because the nucleus is unstable. We refer to those as radioisotopes, and the reason why a nuclei can be unstable is because they have too many neutrons or too many protons in the nucleus. When this happens, they undergo radioactive decay to become more stable, and the nuclei emits radiation and energy to form stability. The radioactive isotope that is decaying is referred to as the parent isotope, and what happens is the parent isotope will decay and turn into a new isotope, and we call that the daughter isotope. So the newly formed isotope is called a daughter. If you look in this diagram, you start off with an unstable parent isotope, which is also referred to as a radioisotope. It undergoes some form of radioactive decay, and it produces daughter isotopes, and there's 3 ways in which that can happen. The first type of decay is called alpha decay. Alpha decay, and I would ask that you copy this chart into your notes. Alpha decay is described as 2 protons and 2 neutrons leaving the nucleus. So the nucleus just has too many of both, and it ejects 2 of each subatomic particle from the nucleus to gain stability. We refer to that as a helium nuclei because helium is number 2 on the periodic table. It has 2 protons and 2 neutrons. And so we just say that in alpha decay, a helium particle is ejected from the nucleus. Alpha decay is the least harmful type of decay because it is the most easily blocked. Alpha decay can be blocked by just a piece of paper, and even the clothing that you're wearing has the ability to actively block alpha decay particles. The second type of radiation is beta decay. Beta decay is a little stronger, and it takes like a thin piece of metal, aluminum or tin, to block beta particles. And beta particles are a little bit more complicated, so we'll talk about those in a minute. The last type of radiation is gamma rays. So gamma rays aren't actually particles. They are high energy electromagnetic radiation, and it's associated with both alpha and beta decay. So whenever alpha and beta decay happen, gamma rays are also produced. These are the most dangerous, and the penetrating power, or the ability to go through things, you really need to have a very thick concrete wall or piece of lead to block the gamma radiation. So these particles were discovered using the electric field effect, which was an experiment designed to determine the charge of these particles. And what happened is positively charged particles deflected toward negative charge, the negative charge deflected towards the positive side, and the gamma rays weren't affected at all. So I'll ask that you click on this electric field experiment to watch the video to show how this works before moving on to the next slide. So revisiting the alpha particle, here's an example of an alpha reaction. So it's a nuclear reaction of radium-226, which is the mass number of that radium isotope, and what happens is it undergoes alpha decay. When radium-226 undergoes alpha decay, it's going to eject 2 neutrons and 2 protons from its nucleus to become more stable. You can see in the picture that radium goes from 226 down to 222, and that's its mass number. So because it's ejecting 2 protons and 2 neutrons, its mass number is going to be reduced by 4, and the atomic number, or the bottom number, goes from 88 to 86. So that's because you only lost 2 protons. And then you also eject that helium alpha particle out of the nucleus. The way that you would write an alpha decay equation, if you look at my example in the bottom left, you have polonium-210, which has an atomic number of 84, it's number 84 on the periodic table, it undergoes alpha decay. It loses that 4,2 helium particle, and its top number, 110, drops by 4 down to 206, and the bottom number, 84, drops by 2 down to 82. Beta particles are a little interesting. What happens is if you look at this example, iodine 131 undergoes beta decay. It loses a beta particle, and you can see that the beta particle symbol is 0, negative 1b. What happens is it ejects an electron produced by a neutron from an unstable nucleus. Beta radiation consists of fast-moving electrons that stream out of a nucleus until it becomes more stable. So you can see in this situation, iodine 131 turns into xenon 131, and you notice that the top number doesn't change, and the bottom number increases by 1. So let me explain how that works, because this is a little complicated. This change in atomic number occurs because a neutron in the nucleus turns into a proton and an electron, and then the electron gets ejected from the nucleus, leaving behind a proton. So the neutron turns into a proton and ejects an electron. So if a neutron turns into a proton, then the mass number won't change. But if a neutron turns into a proton, the atomic number is going to increase by 1. So if you look at the beta decay equation on the bottom left, carbon 14, the mass number is 14, that means it has 8 neutrons and 6 protons, turns into nitrogen 14 through beta decay, but one of those neutrons turned into a proton, so the atomic number increased to 7, making it nitrogen. So carbon can actually turn into nitrogen through beta decay, and then you can see the beta decay symbol next to the nitrogen. Lastly, you have gamma rays or gamma radiation. Gamma radiation is high energy, short wavelength electromagnetic radiation. It is the highest frequency on the electromagnetic spectrum next to X-rays. So if you look at the electromagnetic spectrum on the far right, that's where you have your gamma rays. So they're the most dangerous and hardest to prevent from penetrating into human bodies. And gamma radiation or gamma rays is associated with the 00Y symbol. That Y stands for gamma, and it is high energy radiation that is coupled with alpha and beta decay. So it occurs simultaneously with alpha and beta decay, and it accounts for the energy loss when you have a nuclear reaction. So why does any of this happen to begin with? Everything is about stability. As the atomic number increases on the periodic table, more and more neutrons are needed to overcome or create the strong nuclear force within the nucleus to hold all those protons in there. So if you have a really large atom that has 82 protons, you're going to need a lot of neutrons to create that strong nuclear force. So the neutron to proton ratio increases as the atoms get larger, and what happens is if the ratio of neutrons to protons reaches 1.5 to 1, that's when it becomes unstable. The proton-neutron ratio really likes to be a 1-to-1 ratio, so if you have 6 protons, having 6 neutrons makes it something, a carbon atom, because that has 6 protons, very stable. But the further away you get from that 1-to-1 ratio, the more unstable the isotope becomes and the more likely it is to decay. So as an example, lead-206 has 124 neutrons and 82 protons. If you take the 124 and divide it by 82, you're going to get the number 1.51. So that means that the neutrons are 1.51 to a proton-1 ratio. That's an extremely unstable nuclei, and it's going to undergo decay. So here's just a quick overview of how to calculate stability. So again, using that lead-206 example, it has 82 protons, and the mass number is 206, so you'd have to subtract 82 off of 206, and you end up with 124 neutrons. And so 124 divided by 82 gets you that 1.5 to 1 ratio. And that tells us absolutely this is an unstable isotope and it will undergo decay. You also have this graph, it's called the band of stability. If you could put a sketch of this graph into your notebook, it's important. 82, 83 on the periodic table, it shows you the number of protons, which is on the x-axis, compared to the number of neutrons on the y-axis, and it plots them, and it plots the band of stability. So you can see as you go up, the ratio gets further and further away from the 1-to-1 ratio, and the reason why elements 84 and above are not plotted on this graph is because they are all radioactive no matter what. So all of those really, really large elements are radioactive, and so they don't even make it onto the band of stability because they're going to be radioactive. So after each atom decays, either through alpha or beta decay, it forms a new atom, which is the daughter isotope. And when that daughter isotope is formed, it's able to be more closely aligned with that 1-to-1 ratio and maintain or gain stability. And so the purpose of radioactive decay is to eject particles out of the nucleus to get closer to a 1-to-1 neutron-proton ratio in order to gain stability.